Hello and welcome. Today is March 23rd, Monday. We have lots of work to do today. We need to catch up on a few things. We're like about 2 days behind, but that's all right. We can always catch up to last year's kids. Today we're going to go over what we started with Biot-Savart law last time, and we also did Amperes law. This was the this was the the magnetic field inside the wire, based on some sort of current density function, how much current you get per area. We started off with some arbitrary small amount, little r, and then as you expand little r outwards, to eventually becoming capital big R, which is the maximum radius of the wire, then you get you get a linear equation inside of the wire, and then it falls off at a 1 over r rate. We have a lot of things to do today. I'll take other questions at the end of the session, so hold on to your random questions until the Q&A session. But for now, let's focus on the actual content. All right. So anyway, instead of just having a single wire, we want to loop this around. So we're going to find B from a looped wire. Okay. And by looping it, we create a circle which looks like a magnetic field. Recall that magnetic fields, here's a compass, so we get the magnetic field by using a small small compass. So, whoa, look, the compass points in the direction of the magnetic field, but it has to be strong enough. So let's see, let's show the field. Boom, here's the field. Whoa, each point is represented by a tiny little compass. So if I put my compass next to the South Pole, it goes into the compass, of course. Here at the middle, it turns nice and flat, horizontal. It's tangent to the arc. Okay, and it goes out of the north into the south. Notice how the north end, this north arrow, will bend. It goes into the south end of the compass, comes out of the north end of the compass, and then it eventually goes back into the south end of the magnet. Okay, we can show the field meter. So this is measuring the value measuring the value of B. B is the total, the resultant vector. There's By, Bx. There's also theta, the direction of the magnetic field at each point. Okay. There's a unit of capital G, which is a non-standard unit. Anyone know what the unit capital G is for? It's named after a famous. Actually, we've been using his law for quite some time now, for other things. Okay. Capital G is the Gauss. Yep. And 1 Tesla is equal to 10,000 Gauss. Okay, so it's 1/10,000th, or 1 times 10 to the -4. Alright, anyway, so that's that. Let's go and create our looped wire. We're going to do this in 3D, so get your calculus pants on. It's going to be a bumpy ride today. Similar to how we did the electric field at some point from a loop, we're now going to do the magnetic field. Let's make this the z-axis such that we are z distance away, a constant z distance away at the center of a looped wire that is on the xy plane. Okay. First, we need to establish the direction of current. So let's say current is looping around this way. Okay. So without this current, we wouldn't have a magnetic field. Now, how is it, getting current if it's not connected to a battery or something? But you gotta use some artistic licensing, some creativity. Typically, when you make a loop, what you would do is make it like a lollipop, in that you go straight up with a wire, make your loop, and then come back down as close as you can to the first wire, and then go down again. So this is essentially the same thing. But we're only going to focus on the loop part. Okay, so let's consider a tiny little portion down here, and you'll see that this portion is some distance away. We'll call it little r. Okay, and the maximum distance, which is a constant distance from the center of the loop, and let's go and say that the radius of the loop itself is capital R. Okay, and you'll see that no matter where you grab the wire, remember, we're using right-hand rule number 1 to find the magnetic field around a current-carrying wire, in this case a current-carrying loop. No matter where you grab it, you'll see that the thumb, of course, points in the direction of the current. The fingers will go outwards to the right on the inside of the loop. Okay, go and use right-hand rule number 1 to grab this loop. If you grab it at the top, you need to point your fingers towards you, I suppose, and you'll see that the fingers curl all the way around and point in the positive z-axis. Our z-axis is to the right here. Okay, this creates a magnetic field, like a cone shape, kind of like the electric field. But all of the y components cancel out, leaving you with just the x component, or sorry, the z component. Okay, meaning there is no magnetic field in the other axes, it's just all in the z axis. Okay, let's call this angle theta. All right. Now, for those of you who are in multi, this part may be a little bit more important. Okay, the r hat vector is that way. You would definitely need this if you want to major in physics. The r hat vector is that way. Which way is the dl vector? Well, dl vector is going to be chosen in the same direction as the current itself. Remember, we set the current value at a constant value, and we use dl as our vector when we're doing our cross product. So dl is in towards the x-axis, and this is a small chunk of length, dl. All right. So the r hat, remember, it points from the actual particle or from the actual spot inside your loop, inside your wire, the infinitesimal amount of charge that is passing through, from that towards the point in question. So we are trying to find the magnetic field at some point that is z distance away on the z-axis. So that's our r hat direction. And the angle between our r hat and our dl, as we take the cross product. Okay. All right. And of course, at the top side, let's go and focus on the top side now. At the top side, we would have a dl vector that points this way. Okay. And we have our r hat vector that points towards, so let's use red again. So we draw a line that goes from our infinitesimal amount of dl towards our dot, and our r hat vector would be this way. Okay, so now we need to use our Biot-Savart law to add up all of the infinitesimal magnetic fields that we get from each little chunk. Why is it dl and not di? We're setting I as constant, so it's a constant value current. The current is not changing, the amount of current is not changing. And dl goes around the loop, so we will add up all of the dl's. We want to find our magnetic field from each infinitesimal amount of L, some distance away from that L. Okay, so that's our general formula for the Biot-Savart law. Recall that dB, in this case we're just doing dBz. Oh, dBz! The infinitesimal amount of magnetic field in the z-axis. It was all planned. Isn't I all around, and that box is only a portion of L, a dl amount? So L is like the length of the little piece. Yes. L is the dl is the length. In this case, it's a little tiny arc length. And you'll see in a moment, when I add up all the dl's, you're going to get a whole circle. It's the circumference of the circle. When I integrate every little tiny little thing. Liam, finally. Wake up, Liam. Get some coffee. You got to be ready by 11. Come on now. So yeah, so remember the BLI for the force. Right now we're just doing the I and the L part. Can you see my message? Yes, you're not banned. All right, so what is dBz? Well, dBz, z-axis, is going to give us, okay, our Biot-Savart law, which is mu naught I over 4 pi r squared, r being the distance away from your little length, times dl sine theta, right? Where do we get dl sine theta? Well, that's from the cross product. This piece here, we'll use green. This is from the dl cross r hat. That's how the Biot-Savart law is written. It's written in your in your book. I have to use VPN to chat. What? No, you don't. Oh, well, stop using that one. Wow, it does? I didn't know it IP bans you. That's really cool. Wow. Why isn't DLR sine theta? No, it's not R. This is R hat. Okay? These are called unit vectors. These are not the actual magnitude of a vector. It's r hat. R hat is a unit vector, which means it's basically 1 in the direction of r. So r hat means 1 in the direction of r. That's what it means. Okay, so it's 1 times dl, and that's what dl is. But the direction of r is 1 times sine of theta. Because it's a cross product. So dl times 1 times sine of theta gives you the cross product. No. Yeah, there you go. Mystery Wizard, thank you very much. Remember, cross product is A vector cross B vector is equal to, at least for the magnitude part, is equal to A times B times sine of the angle between A and B. Okay? So strategically, we're using r hat, because that's a unit vector, which automatically has a value of 1. So we're doing A times 1 times the sine of the angle between A and R. Mystery Wizard is not Nishank. Didn't we confirm that? The Mystery Wizard was Alex Frank, wasn't it? Okay. No, you don't get to use my name. How dare you? Alright. Anyway, there you go. That's Nishank. I need 1080p. Yeah, I downgraded the bitrate to 3500 3500 kbps, or 2.5 megabits per second, streaming at 720. This will allow us to get more viewers, I guess, because some people were complaining about freezing and whatnot. All right. Anyway, moving on. Let's go and do some quick geometry and stuff, or trig. Okay. Notice how the sine of the angle. So this angle here can be represented as, let's see, dB. Oops. As opposite over hypotenuse. Opposite over hypotenuse. So we get mu naught I over 4 pi r squared times dl. I'm going to put the sine of theta first. Times sine of theta, that's opposite over hypotenuse. The opposite is capital R. The hypotenuse is little r. I'm using Streamlabs OBS. Times dl. There we go. All right. And then last but not least, we need to integrate both sides. So you integrate closed loop integral, closed loop integral. This will allow us to take off all of the constants out of the integral. This just gives us mu naught I over 4 pi r squared times r. Now, what is r? R, based on the constants that are given, r is the Pythagorean, which is a square root of capital R squared plus z squared, or we are z distance away. So this gives us z squared plus r squared. It's the square root of that, but we have to square it. So that gets rid of the square root. Times r, which is a constant, divided by r again, but this time there's no square. So that's z squared plus r squared, like so. No, we don't want to use r cubed. We want to use the constants that are given, which is the constant distance z from the loop and the constant capital R. All right. And so the only integral we're doing is the closed loop integral of dl. And so if I add up all the tiny l's as I go around a circle, what does dl give me? dl gives me the 2 pi r. So we get mu naught I times r over 4 pi. Let's go and simplify this. This is z squared plus r squared to the 3/2 times the closed loop integral of dl, which is 2 pi. Which r? Chat, type in which r for the circumference. Ooh. Capital R, very good. It is capital R. So this was all just a simple geometry question if the only integral is dl. Yes. Good job, Ved. All right. And the pi's cancel. Pew, pew. The 2's can simplify with the 4. We get an r squared at the top. That was easy. But it's all about, application. I don't want you to start memorizing this. It's about applying how we did this to new situations, to new encounters. All right, that's what it's all about. It's about the problem solving. Okay, so that is our magnetic field. This is B, Z at center. All right. Now, one loop is not very realistic. It's not very strong. Of course, using crazy stuff like let's go. Let's shrink Z as we approach the center. When you go all the way inside, what do you get? Well, as Z goes to 0, what happens? As Z goes to 0, we get 0 plus r squared. R squared to the 3/2 is just r cubed, and the r squared and the top cancel, so you get mu naught 1/2 mu naught I over r. Haha jokes. Nishank has left the chat. What? Wait, what? I squared? What do you mean I squared r? No, it's IR squared. What? Oh, how is it I squared, buddy? IR squared was power? Ooh. No, this is not resistance. It has nothing to do with resistance. R is the... Oh, jeepers. R is the radius, the maximum radius of our loop. Let's go back to the diagram. I think you came in late or something, but I did explain this diagram. Of course, with Twitch, you can go back to the video section at the top. You can click on video and just watch the stream from the start. And then as you catch up to live, then you can come back to live. Okay, this is why you got banned, Jacob. You're repeating your mistakes. You're going to get banned again. Hostile work environment. Alright. How did you get the original DB? How do you catch up? Okay, at the top you click on video, and then you can watch. As I'm recording, you can actually watch up to the point where you actually click the button. So as soon as you click video and you go into the video of today's video, you'll see that your video ends at exactly when you clicked it. So you can just watch it as quickly as possible, skim it, and then catch up to live. Well, you have to skip as you watch because, obviously, for example, notice how I'm spending time explaining this. So if you're watching the video, you can skip this portion. It allows you to time travel. All right. Anyway, let's go and do multiple. You guys are slowing me down. Let's keep going. What if we had multiple loops? Whoa. All right. Well, if I had multiple loops all squished together, then we can just multiply it by n. So B of coil at the center must equal mu naught over 2. Remember, z is now 0. The r squares of the numerator cancels. So we have I over r. R is not resistance, it's the radius. Times n. Okay, or you could write it as mu naught in over 2r. Mu naught in. Yeah, that's where we're headed. Okay. So let's say you have squished everything, and realistically what you would do is create a solenoid. Now on the inside of a solenoid, your book has a really cool picture of this in the solenoid section, and under 29.6 Amperes Law in solenoids, which shows you the derivation of what we're about to do. It shows you the coils drawn like so. So imagine us cutting the solenoid in half so that you can see the wire, the cross section of the wire like this. Ooh, I don't like that one. It's a terrible noodle. There we go. So you were blocked from using the word. It's THOUGHT, buddy. Just got a 7. Wait, I have a question. We'd go over this after the AP test at this point. Why? No, we're not cutting stuff out. Your final's going to be everything. But when we prep for the AP, it'll be up to the AP. The class is more than about a simple, stupid AP test. This class is about producing the future engineers and scientists of our society that will go on and work for companies like NASA and SpaceX. Okay, so that when you become an engineer, when you start your classes as an electrical engineer or whatever it is, or BME, you should be able to go into class without a hitch. No company is going to say, oh, due to this crazy coronavirus thing, let me just give you this job even though you don't know what you're doing. No one's going to say that. So I'm going to still teach you everything. Again, we'll learn all the content, of course, and then our focus for the AP test will shift so that we only cover the essentials. So that yes, you're going to get your star, but you're going to do well in life, which is much more important than the stupid star. . L Mayo, I don't know what to do anymore. Star greater than future? No, no. What? I just saw them in my following. Huh? What are you guys talking about? Bruh, Steven, best tournament organizer is this? So how come you multiply it by n if the loops have different distances from the point of interest? No, this is a stack of loops. That's when we multiply by n. Imagine basically having multiple loops at the exact same, for this one, we have to kind of stack them up. And we also have to ensure that all the r's are essentially the same or negligible in difference. Okay. But when you use wires, we have to use some sort of insulation, and that insulation kind of spaces out our wires, so it's almost impossible. So that we have a solenoid like this. So the solenoid will have a little bit of gap, and that gap is going to be based on how much insulation or how thick your wire is, essentially. So you're going to have some sort of gap like that. Okay, and this is where I would also reference a picture of the solenoid, the real one, figure 29.30. So I'll check figure 29.30. They show you, some iron shavings around a solenoid. This is a really cool demonstration that we cannot, unfortunately, do at this time over the air. But anyway, check figure 29.30. It shows you some iron shavings around a solenoid. Okay. So the idea for solenoid is that the magnetic field all go through one direction. Any one direction fans? There's only one song that I approve of, the one where they did it at NASA. Anyway, the magnetic field goes through our solenoid. Of course, the direction of the current will matter. So let's ask a question in chat. Notice how my loop. Let's try that again. Here's my loop. It goes this way, around, like so. In order to get a magnetic field to the right, which way is the current going in? Is it upwards this way, option 1, or is it downwards this way, option 2? Ooh. Hold on, let's do a Streamlabs vote. How do I do this? Poll. There we go. Option 1, edit. Current. Vote 1 for up, or vote 2 for down. Let me go and start it. Start poll. All right, we got some. So you have to do vote and then number. So something like that. Oh wait, lowercase. Yeah, lowercase. We already got one vote. Oh, it's 50-50 split. Whoa. Can I show you? No, I can't. Oh yeah, I can. I can show you. Here, let me show you. Here's my Streamlabs. Oh no, I can't show you. It just it goes crazy. All right, I'm closing the poll in 5, 4, 3, 2, 1, and 0. Close. Oh my gosh, we are literally. We are bad. We literally guessed. All right. Use your right hand rule number 1. Okay. In order to get magnetic field through the inside of the coil, it has to go this way, up. Option 1. Okay. So that your thumb points upwards, and you'll see that the fingers curl around and come outwards like this on the inside of the hoop. All right. Anyway, to do this, I am the new knee shank. Wow, you've been dethroned, Mr. President. You've been dethroned. All right. So, what we want to do is create a DL. So let's go and create a DL, a closed loop. We're going to do a closed loop like this. Here's our closed loop. Okay. Our closed loop goes this way. Like so. This is our loop. Okay. And we are some L distance in size. Okay. Essentially, what you would do is make this closed loop so that it encompasses the entire solenoid, however big your solenoid is. But we're just doing it as a little tiny piece. What's interesting is that no matter how big you make this loop, it doesn't really matter whether you cover the entire solenoid or just do a small portion. Okay. So again, if you encompass the entire solenoid, then you use L as the length of the entire solenoid. So we're going to do a nice square, and it has to be symmetric. Let's make it nice and symmetric here. Well, technically, it doesn't have to be a square. Sorry. You can make it as symmetric in that it's 90 degrees. That's what I meant. Notice how the B vector here, okay, B is in the same direction as DL when you're on the inside. So inside, DL is in the same direction as your magnetic field. Okay. Now on the sides here, this one and this one, it is 90 degrees. Sides, DL is 90 degrees to B. Okay. And finally, on the outside, we hold that the magnetic field is 0 on the outside for ideal solenoids. Okay. Why is the outside of a solenoid 0? Well, let's see if we can explain that one. Imagine having a magnetic field from each loop. Okay, since the current is, let's say the current, oops, I have current coming out of the page both ways. Let's make current going in this way. Okay, if you take a look at our original drawing, right, it's going into the board on the bottom side, and then at the top side it must be coming out of the board, the current. So I have X's down below and dots up top. Okay, if I do that, current is coming out. Notice how the magnetic field vector would be a circle that looks like this. Okay, but this second one would also have a circle that looks like this. And so this vector and this vector here would cancel each other out, leaving you with just the X components alone. So notice how the X component is to the right, the X component is to the right, the Y component is up, the Y component is down, so all of this stuff is canceled out. On the outside, we have X to the left, and on this one, oops, I shouldn't do that. If you look at the vector drawing Where is it? This is figure 29.29. 29.29 figure. Oops, fig. And you'll see how the third one, here, let's see. So let's say this thing keeps going and it's some direction this way at this spot here. Let's see. Okay, let's use dark blue for the first one. And I'll use green. No, 29.29. 30 was the last one. Okay, 30 is to see the real solenoid. Okay, take a look at 29.29 now. The fields of the three loops nearly cancel here. That's because the second one, let's use green, it curls around, and so it has a vector that points to the left. That's from the second one. And I'll use magenta or red. Let's use red. For the third one, as you curl, the third one gives you a vector that is pointed downwards to the right. So red is from this loop here, blue is from the first loop, and green is from the second loop. Okay, so the green leftward arrow cancels out the two X components from the blue one and the red one. And of course the Y components cancel each other out anyway, giving you 0, a B field outside. Oop, 1 second. All right, I need to be done pretty soon. So anyway, so the outside is 0. I can always turn this down. There we go. So the outside is 0. So now we can go back to our DL. The only thing we have to worry about is the bottom of the DL here, because that's where the magnetic field is in the same direction. And we're going to go ahead and use Amperes Law. What is Amperes Law? Can someone tell us what Amperes Law is? Amperes Law is closed loop integral B dot, it's a dot product, DL is equal to mu naught times I through, or, you know, this is another way of saying like Q enclosed. It's basically Gauss's law for magnetism. So the dot product of perpendicular vectors give you 0. The dot product of parallel vectors, but where the magnitude is 0, also gives you 0. So the only dot product we have to worry about is the inside. Okay, the inside. And this is where we get our solenoid equation. So B dot DL. If I add in all of the DLs, so let's take a look at this diagram again if I can fix it. Okay, we're going to add each little infinitesimal amount of chunk here. This is a DL plus the next DL. Essentially, all the little tiny DLs gives us the size of your solenoid, capital L. So B times capital L must equal mu naught times I, but we have multiple. This is only for one loop, or one loop. But if I had multiple, I would just have to, linearly multiply by n. Yeah, mu n. And so the solenoid is B over mu naught n over L, and we say n over L is the loop density. Loops per length. All right. That's it for Amperes and Biot-Savart. Your mastering physics is very challenging, so make sure you get started. There's a square loop question, where you have to find the magnetic field somewhere inside or something like that. For the square loop magnetic field question, you're using Biot-Savart law, but for 4 pieces, 4 wires basically. So you have to do 4 integrals. Not the easy one, not Gauss's, but 4 Biot-Savarts, and figure out what the net result is. Fantastic. Yeah, that thing takes like half an hour. Good luck. Tomorrow we're going to move on to charge. We'll talk about force on charge, right-hand rule number 3, cyclotrons, and that should be it for chapter 29. And then on Wednesday we will start with chapter 30, induction, talk about motors and how to make motors, etc. All right, I'm going to end the stream, and then I'll take some Q&A afterwards. Thank you for tuning in. I'll see you next time.